So in this class we will study about emitter bias circuit. In previous class we have studied about fixed bias circuit. Okay. So the circuit diagram for emitter bias circuit, it is like this. This is RB, this is RC, and this is emitter resistor. This is VCC. So current IE, current IB, and current IC. Okay. So this is the circuit diagram of emitter bias circuit. Okay. So the difference between fixed bias circuit and emitter bias circuit is that in emitter bias circuit one extra resistor, that is RE, is connected here to the emitter. This is emitter terminal, this is base terminal, and this is collector terminal. Okay. So this is the circuit diagram of emitter bias circuit. Okay. So for this emitter bias circuit, suppose we want to apply Kirchhoff's voltage law in base emitter loop. Then how we can write down the equation? It is VCC, it is equal to IB RB plus VBE plus IE RE. This is the equation by using Kirchhoff's voltage law in base emitter loop, in this loop, input side. Okay. So it is VCC, it is equal to IB RB plus VBE plus IE RE. Okay. Now we know that IE, it is equal to IB plus IC. Okay. So it can be written like this. It is IB plus IC, it is equal to beta times IB. Okay. So we can put this value of IE here. Okay. So it is equal to VCC, it is equal to IB RB plus VBE plus IB plus beta IB into RE, like this. So it is equal to IB RB plus RE plus beta RE plus VBE. We can write this equation like this. So from this we can determine the value of IB. So IB, it is equal to VCC minus VBE divided by RB plus 1 plus beta RE. So this is the expression of IB, the current IB in emitter bias circuit. IB, it is equal to VCC minus VBE divided by RB plus 1 plus beta RE. So in fixed bias, the expression of IB, it is equal to VCC minus VBE divided by RB only. But in emitter bias circuit, because of the use of or because of connecting RE, resistor RE, IB now it has changed to VCC minus VBE divided by RB plus this term. This term it is increased. Okay, so this is the difference. This is the difference between emitter bias circuit and fixed bias circuit. In fixed bias circuit, this term is absent, but in case of emitter bias circuit, here it is 1 plus beta RE. This term it is present. Okay. Now we can determine IC, it is equal to beta times IB. Okay. So motive is to determine the Q point. Okay. So IC and VCE we have to determine. So IC can be determined if IB is determined. So IC we can determine like this. Now how to determine VCE? Okay. So in order to determine VCE, we have to consider the outside loop, that is collector emitter loop. Okay. So it is VCC, it is equal to ICRC plus VCE plus IERE. We can write like this. So it can be written like this: ICRC plus VCE plus IE. IE is approximately equal to IC. So we can write ICRE. So finally it is equal to ICRC plus RE plus VCE. So from this equation, how we can determine VCE? VCE it is equal to VCC minus IC RC plus RE. So in this way we can determine the Q point or operating point. So IC it is equal to beta IB, and how to determine VCE? VCE it is equal to VCC minus IC into RC plus RE. So in this way we can determine both the operating point IC and VCE. So once we determine IB, then we can determine IC, and from the output loop, that is collector emitter loop, so we can determine VCE from this equation. So in this way we can determine IC and VCE. Okay. Then we can see the same circuit. This is RC and this is RB and this is RE. Okay, and it is connected to VCC. So this is the circuit diagram of emitter bias circuit. Okay, so we have determined IC and VCE. Okay, now how we can determine voltage at point E, voltage at point B and voltage at point C. So VE it is equal to voltage of this point with respect to ground. So it is equal to IE into RE. The current it is IE. Here the current is IC. Here the current is IB. Okay, and we know that IE is approximately equal to IC. So VE is also equal to IC into RE. Okay. Now how we can determine voltage at point C? VC it is equal to VCC minus ICRC, or another method, VCE, it is equal to voltage at C minus voltage at E, always with respect to this ground. Voltage of C with respect to ground minus voltage of E with respect to ground. So from this equation we can get VC, it is equal to VCE plus VE. In this way we can determine voltage at C. Then how we can determine voltage at point B? Voltage at point B. So we can write VBE, it is equal to VB minus VE. So from this equation we can determine VB, it is equal to VBE plus VE. Now in forward bias, suppose base emitter is in forward bias condition, and if this transistor is made up of silicon, then in that case VBE, it is equal to 0.7 volt, and if this transistor is made up of germanium, then in that case VBE, it will be equal to 0.3 volt. Okay, so in this way we can determine voltage at point B. Then another method, how we can determine VB, it is equal to VCC minus IB RB. From this expression also we can determine voltage at point P. It is equal to VCC minus IB RB. So it is equal to VB. So in this way we can determine voltage at point B, voltage at point C, and voltage at point E. Okay. Load line analysis. Okay, load line analysis for this emitter bias circuit. This is emitter bias circuit. Okay, so in load line analysis, it is the graph between IC versus VCE. Okay, so the expression in the output side, it is equal to VCC, it is equal to IC RC plus VCE plus IE into RE. Okay, so it is equal to IC RC plus VCE, and since IE is approximately equal to IC, so we can write here plus IC into RE. So it is equal to IC RC plus RE plus VCE. So from this equation we can write the expression for VCE, it is equal to VCC minus IC into RC plus RE. Okay, so how we can plot the load line? Okay, so for plotting load line for IC, if IC is equal to 0, if IC is equal to 0, then VCE, it is equal to VCC. So in this axis, horizontal axis, that is on VCE axis, IC is equal to 0. So if IC is equal to 0, VCE, it is equal to VCC. So suppose this point is your VCC. Okay, so we can get 1 point. Okay, we can write if VCE, it is equal to 0, then IC, it is equal to VCC divided by RC plus RE. Okay, so this point is it is equal to VCC divided by RC plus RE. Now we can connect these 2 points. So this is the DC load line of emitter bias circuit. Okay, this side it is VCC. This point is VCC divided by RC plus RE. Okay. Now the output characteristics is like this. Suppose this is IB1, IB2, IB3, IB4 and then IB5. Okay. So how we can determine the Q point? By selecting IB. By selecting IB, we can determine the Q point. Suppose IB3 is the desired value of IB current. So the Q point it is like this. So value of ICQ and value of VCEQ it can be determined from this load line. Okay. Stability factor in case of emitter bias circuit. Okay, in emitter bias circuit. How we can determine the stability factor? So the expression for stability factor it is equal to del IC divided by del ICBO. It is equal to 1 plus beta divided by 1 minus beta into del IB divided by del IC. This is the expression of stability factor with respect to ICBO when beta and VBE both are constant. Here beta and VBE both are constant. VBE or IB both are constant. Okay. So how we can determine the stability factor in this emitter bias circuit? Okay. So in order to determine the stability factor, we have to determine this value delta IB divided by delta IC. Stability factor as it is equal to circuit. For this circuit, say this is emitter bias circuit. This is RB. It is connected to VCC. This is RC and this is RE. Okay. Now VCC it is equal to IB RB plus VBE plus IE into RE. We can write like this. Suppose the current it is IE, the current it is IB and this current is IC. Okay. So it is equal to IB RB plus VBE. Now IE is equal to IB plus IC multiplied with RE. We can write IE it is equal to IB plus IC. We know that the emitter current it is equal to base current plus collector current. From this figure also we can see IB plus IC it is always equal to IE. Okay. So this equation we can write like this. VCC it is equal to IB multiplied with RB plus RE plus BBE plus IC into RE. Okay, so we can write BCC minus BBE, it is equal to IB RB plus RE plus IC RE. Suppose this equation is A. Okay, now differentiate both left hand side and right hand side by this del by del IC. Okay, so what we will get, it will be equal to 0 because this is constant and BBE is constant. BBE we have del IB by del IC, we have fixed it at beta is constant and BBE is constant. So here BBE is independent of IC. So it is 0 minus 0, it is equal to del IB by del IC into RB plus RE plus del IC divided by del IC, it is equal to RE. So we will get del IB divided by del IC, it is equal to minus RE divided by RB plus RE. Okay, so this is the expression of del IB by del IC. So how we can calculate the stability factor, that is S. S is equal to 1 plus beta divided by 1 minus beta into del IB by del IC. Just now we have calculated del IB by del IC, it is equal to minus RE divided by RB plus RE. Okay, so we can calculate as it is equal to 1 plus beta divided by 1 minus beta multiplied with minus RE divided by RB plus RE. Okay, so we will get the expression for stability factor as it is equal to 1 plus beta divided by 1 plus beta into RE divided by RB plus RE. Okay, so this expression we can write it like this, it is equal to 1 plus beta 1, it is 1 plus RB divided by RE, it is 1 plus beta plus RB divided by RE. Okay, so this is the expression of stability factor in case of emitter bias circuit. Okay, now what is the range of this stability factor? If RB by RE is very small, if RB by RE it is very small, then S will be equal to 1, because in that case RB by RE, okay, we can write if RB by RE it is very small, okay, if it is approximately equal to 0, then in that case S it is equal to 1. And if RB by RE, if it is very high, if RB by RE is very high, then S it is approximately equal to 1 plus beta. So the stability factor, it varies from 1 to 1 plus beta. 1 when RB by RE is very small value, and 1 plus beta if RB by RE this value is very high. Okay, so in this way we can determine the stability factor. Okay, so as compared to fixed bias circuit, okay, here we are seeing the stability factor, it is less as compared to fixed bias circuit. See, in fixed bias circuit, the stability factor as it is always equal to 1 plus beta. But here in case of emitter bias circuit, stability factor can be decreased. Its value it is from 1 to 1 plus beta. Okay, it can be decreased or it can be increased by varying RB by RE ratio. If this ratio we can vary, then definitely S will be varied. Okay, and as compared to fixed bias circuit, the stability factor it is low here. Okay, now we will see this example. This circuit is emitter bias circuit. Okay, so in this emitter bias circuit, the beta of this transistor it is 50 and it is made up of silicon. Okay, and the value of RB, the value of RC, and the value of RE it is given, and value of VCC it is also given. Okay, so we have to determine these values. What is the value of IB? Okay, so how we can determine it? We can determine it like this. Okay, so the expression for IB it is equal to VCC minus VBE divided by RB plus 1 plus beta multiplied with RE. We can write it is 20 volt minus 0.7 volt. Why this 0.7 volt? Because it is in forward bias case and this is made up of silicon. This is silicon based BJT. Okay, so it is 0.7 volt. RB it is given as 430 kilo ohm plus 1 plus 50 multiplied with RE. RE is 1 kilo ohm. So it is equal to 40.1 microampere. So it is equal to 40.1 microampere. Then we have to determine IC. How we can determine IC? Once we have determined IB, so we can determine IC like this. IC it is equal to beta times IB. So beta is given as 50 and IB is 40.1 microampere. So it is 2.01 milliampere. It is 2.01 milliampere. So we can write here IC is equal to 2.01 milliampere. Okay. Now we have to determine VCE. How we can determine VCE? VCE can be determined by applying Kirchhoff's voltage law in this path. Okay, VCC it is equal to ICRC plus VCE plus IE into RE. So it can be written like this. plus IC into RE, because IE and IC both are approximately equal. So it is equal to IC RC plus RE plus VCE. So from this we can determine VCE, it is equal to VCC minus IC into RC plus RE. Okay, so VCE it is equal to VCC, it is equal to 20 volt minus IC is 2.01 milliampere, RC plus RE, RC is given as 2 kilo ohm plus RE is 1 kilo ohm, so it is 3 kilo ohm. Okay, so finally we are getting VCE, it is equal to 13.97. Okay, after calculation, so it is equal to 13.97 volt. Then how we can calculate VC? Voltage at point, this point C, this is point C, this is base terminal and this is emitter terminal. So voltage at C, voltage at point C, it is equal to VCC minus IC into RC, or VCE, it is equal to VC minus VE. So from this equation we can write VC, it is equal to VCE plus VE. So there are two methods of calculating VC. So voltage at point C, it is equal to VCC minus ICRC. First method, this is your first method, and second method is by using this equation VCE, it is equal to VC minus VE. Okay, so as we know that VCE, it is equal to 13.97. VC we have to determine, and VE, how we can determine VE? VE, it is equal to IE into RE. Okay, so we can determine like this by using first case. Both the cases it will be same. VCC, it is equal to 20 volt minus IC is 2.01 milliampere multiplied with RC. RC is 2 kilo ohm. So 15.98 volt. It is equal to 15.98 volt. This is by using first method. And second method, how we can determine? Second method is VCE, it is equal to VC minus VE. Okay, so VC, it is equal to VCE plus VE. So it is equal to VCE, it is equal to 13.97 volt plus what is VE? VE is, we can write it as IC or IE into RE, and IE is equal to, approximately it is equal to IC into RE. So IC is 2.01, it is 13.97 volt plus it is 2.01 milliampere multiplied with RE. RE is 1 kilo ohm. So it is equal to, if we will calculate it, it will be equal to 15.98 volt. So by using both the two methods, result will be same. So in this way we can determine VC. Then how we can determine VE? Again, by using two methods we can calculate VE. VE, it is equal to IE multiplied with RE. So it is approximately equal to IC into RE, first method. and second method is equal to VCE, it is equal to VC minus VE. Okay, so it is VE, it is equal to VC minus VCE. So by using two methods we can determine the value of VE. It is equal to 2.01 volt. Okay, 2.01 volt. Then how we can determine VB, voltage at point B? We can determine again by two methods. VB, it is equal to VCC minus IB into RB. It is voltage at this point, it is equal to VCC minus this current flowing across this resistor multiplied with this RB. So this is first method, and second method is like VBE, it is equal to VB minus VE. So VB, it is equal to VBE plus VE. So this is second method. By using this method also we can determine VB. So by using both the equations, VB will be same, 2.71 volt. Okay, by using both methods. Okay, then how we can calculate VBC? Okay, so VBC we can calculate VBC. VBC, it is equal to VB minus VC. So VB is given as 2.71 volt, VC is 15.98 volt. So if 13.27 volt, but its value is negative. Okay, so it is minus 13.27 volt. Okay, so in this way we can calculate different values. So we have calculated IB, IC, VCE, VC, VE, VB, VBC. Okay, so in this way we can calculate the different parameters in case of emitter bias circuit. Okay, now we will see another base. This is emitter bias circuit. Emitter bias circuit. Okay, so for this emitter bias circuit we have to calculate, or we have to draw the DC load line. So how we can plot the DC load line? Okay, so in order to plot the DC load line for this circuit, we have to determine the value of IC and we have to determine the value of VCE. Okay, so if IC is equal to 0, in this axis value of IC it is equal to 0, so VCE it is equal to VCC. So this point is VCC. VCC is given as 18 volt, and at this point when VCE is equal to 0 volt, then the value of IC it is equal to VCC divided by RC plus RE, like this, RC plus RE. Okay, so it is equal to VCC divided by RC plus RE. So we are getting this point. Okay, now we have to join these 2 points. So this is DC load line for this circuit. Okay, so in this way we can plot the DC load line for emitter bias circuit. Thank you.